Hello, my geometry class. Today we're going to be taking a look at section 11-7, which is entitled Ratios of Areas. And I would normally encourage you to be following along in your book, but I think today maybe I'll give you some examples that I want you to figure out on your own without using the book. So keep your books closed for at least the first part of this lesson, and then afterwards you can go ahead and look through it all you want. It's a pretty short section. So we've been dealing with the areas of different figures, and a few chapters ago we dealt with ratios. Now we're just going to combine both of those ideas and talk about the ratios of areas. So mostly what this section is going to be is we're going to be taking a figure and we're going to say you have two squares and one of the squares has a side length of 1, the other one has a side length of 4. What is the ratio of their areas going to be? Or if you have any shape, the shape of the state of Ohio, and you kind of make a scale model of it, like 1/1000th the real size or something. What's the ratio of the areas and the ratio of the perimeter is going to be? Those are the sorts of questions that we'll be addressing in this section. So to get you started off, I want to consider with the ratios of what happens to a triangle when we double one of its side lengths or its base or its height or anything like that. So let's say we have, I'll give you an example here, two triangles. This is triangle 1, and we'll make this triangle 2. Both of these triangles are going to have a height of, let's say, 3. We're going to make the first one have a base of, let's say, 4, and the second one is going to have a base length of 8. And note that's the entire base length. I'm going to tell me what the ratio of these areas are going to be. Note the only thing that I am doing is I am doubling the base. So the height stays the same, I'm just doubling the base, and we're going to see what that does. So pause the video if you need to and solve this, and I'll go ahead and show you the answer here. So the area of this first triangle is going to be 1/2 base times height, so 1/2 3 times 4, or 4 times 3 if I go in the same order, which becomes 12 divided by 2, which is 6. And when we doubled the base, we have 8 times 3, and that's all times 1/2. So we end up with 24 divided by 2, which is 12. And this shouldn't be a surprise to us that when we doubled one of the bases, we actually ended up doubling the entire area of the triangle. And if you think about why that is, our formula for the area of a triangle is 1/2 base times height. 1/2 base times height. Let me go ahead and erase this here. And so if you just double that base, so 1/2, and then we have 2 base, so we double the length of the base times height, we just double the entire value. That's 2 times 1/2 base times height. So that's all we really did there. Okay. So that is the first example. Now, I want to consider what happens if we, say, double the height of a triangle and keep the base the same. Let's just work quickly through this. So say we have a triangle with base 4, height 3, and then we have another one that is, let's say, height 6, and the base is still 4. And you can probably make a prediction here pretty quickly as to what's going to happen. We're going to end up doubling the area again. So this becomes 1/2 base times height, 4 times 3, which is 1/2 of 12, which is 6. Then here, once again, we have 1/2 of 4 times 6, which becomes 1/2 of 24, which is equal to 12. And notice, once again, we doubled one of these values, and we ended up doubling the entire area. Okay. So I'll just go ahead and give you the purple box information from page 456 in your book. And it has some of the information that we just went into and a little bit more. So when you're comparing the areas of triangles, these are just some general principles that you should know. The first is that they have the same heights, then the ratio of their bases equals the ratio of their areas. So number 1, so if they have, let's say, congruent bases, or actually the first one is height, let me go in the correct order. If they have congruent heights, so they both have a height of 3 or whatever, then the ratio of their area is equal to the ratio of their bases. So in our example, we found that we had a ratio of 1 to 2, and the area also had a ratio of 1 to 2. Let me see that there. Okay, so that is the first example. The second thing from the purple box is going to be if they have equal bases, and it's the same idea. If two triangles have equal bases, then the ratio of their areas is the ratio of their heights. So if, or I should say congruent bases, then the ratio of their areas is equal to ratio of their heights. Okay, and the third point here, and this is not what we have done yet, but if two triangles are similar, then the ratio of their areas equals the square of their scale factor. So, if two triangles are similar, it's going to be the similar symbol, then the ratio of their areas equals the square of their scale factor. I'll give you an example here in a moment. Ratio of areas equals the square of the scale factor. So let's review a couple things here. Let's review what a scale factor is. So a scale factor is basically how much you're scaling a shape up or down. So I can make a scale model of my house, like 1/1000th the real size. And so if my house is, say, 100 feet long, then it would be 1/10 of a foot, would be the 1,000th length there. It would be the scale factor, would be 1 to 1,000. Now, your scale factor doesn't always have to be 1 to something, it could be 2 to 3. So say I had a, I don't know, like a bike that was 4 feet long, and I wanted to make a 2 to 3 scale factor, like scaled up. I can make one that's 6 feet long. That's a 2 to 3 ratio there. So the scale factor is just the ratio of like one of the corresponding pieces of the two figures. So if I have two triangles that are similar, so all the pieces are in the same ratio. So let's say I have a triangle here that has a, let's say, a height of, I'll go 3 again, and a base of 5. And then I have another one that's going to be bigger. We'll just pretend that's bigger. And it has a height of, let's say, 6 and a base of 10. So both of those pieces are just doubled. Then the ratio of their areas is going to be the square of the scale factor. So right here we have a scale factor of 1 to 2, and if we find the ratio of the areas here, this one becomes base times height over 2, which is 15 halves. The area of this guy here is going to be 6 times 10 over 2, which is 60 halves. And so what we find is this is, well, I'm not going to simplify 15 halves, that's 7.5, and this becomes 30. And 30 is 4 times 15 halves. So the scale factor is 2, and so the ratio of their areas is going to be the square of that scale factor. So had I scaled this up by 3, so let's say I had made this 9 and 15, then suddenly it wouldn't be 60 halves anymore. It would be, see, 9 times 15 divided by 2. And 9 times 15 is 135 over 2. And this is actually 9 times as great as the original. So 15 times 9 is 135. So 15 halves times times 9 is 135 halves. So it's the square of that scale factor there. Okay, let's move on to the next portion here. You're going to have a theorem in this section as well. And I think this theorem is a little more interesting than the purple box, interestingly enough. So this is theorem 11-7. And it's a two-part theorem. So it's assuming that we know the scale factor to two similar figures. So if the scale factor of two, use a similar symbol, similar figures is A to B, then, and then we have two parts here. The first part talks about the ratio of their perimeters. The ratio of their perimeters is just going to be the ratio of their scale factors. So the ratio of perimeters is also A to B. And the second part is the ratio of their areas. Ratio of the areas. That is going to be, and pay careful attention to this, it's going to be A squared to B squared. Now notice both parts of this scale factor here are getting squared. So let's just pick out a simple example. So let's say we have two squares, and these squares have side lengths of 2 and 3. So your task then, and you can pause the video, is to find the ratio of their perimeters and the ratio of their areas. This should not take too long. The perimeter in this first guy here is going to be 2 times 4, because there's 4 2's, and that's going to be 8. The perimeter of the second one is 3 times 4, because there's 4 3's, and that is going to be 12. Now notice the ratio of that. That is going to be 8 to 12. I'm going to put it in fraction form. Now we have to consider what the scale factor between these two shapes is. So the scale factor, you're just going to take two pieces that correspond, so we can take two of these sides since they're squares. It would be 2 to 3. So the scale factor is 2 to 3. And notice that's exactly what 8/12 simplifies to. So 8/12 is 2 to 3. So 2 to 3 is our A to B from up here in the theorem. And so A to B, 2 to 3, 2 to 3, it all holds consistent there. When we look at the areas, it's going to get a little more interesting. So the area of this first square is going to be 2 times 2, which is 4, or 2 squared. The area of this second figure is going to be 3 times 3, which is 9. So our ratio of the areas is going to be 4 to 9. And our theorem up here says that the ratio of the areas is A squared to B squared. We said our A was 2 and our B was 3, and so that would be 2 squared over 3 squared, which is, in fact, without even reducing, 4/9. Now, this will hold true for more complicated shapes as well. It'll hold true for octagons, or in your book there's even like a shape of Texas that it would hold true for. As long as you know the scale factor, you can tell very accurately what the ratio of the perimeters is going to be and what the ratio of the areas is going to be. So let me go ahead and do another example or two here. I think that'd be helpful for us. I'm just going to go ahead and erase everything here. So let's consider, I should just do classroom exercise 1 here. We have kind of two triangles that look about like this. And we know that, actually I'll use a different color here. That length there is 9, and this length here is going to be 5. And so we are asked to tell what the ratios of these two triangles are, and they name them with points, but for sake of time I'm not going to do that. Now, what we notice here is that these triangles actually share a base. And if we look at our purple box on page 456, we know that when triangles share bases, when they have equal bases that is, the ratio of their areas is just going to be the ratio of their heights. So the ratio of the areas of these two guys is going to be 5 to 9. And if you wanted to verify this, you could plug in whatever number you want for the base and then figure out what the area would be. So say the base here was 10. And this is just using our imagination now. Then the area of the big triangle would be 10 times 9 divided by 2, which is 45. And the area of the little triangle would be 5 times 10 divided by 2, which is 25. And 25 to 45 reduces to 5 to 9. So that holds true there. Let's also look at, trying to decide which one to do. Let's look at number 13. Number 13 is an interesting one. This is in the classroom exercises again. So here it's giving you two regions, region 1 and region 2. Let's see what other information we have. This is 2, this is 3, and it gives you points in here as well. And we know that these guys are parallel. I feel like we haven't done a lot of parallel lines in a while. Okay, so the first part of number 13 asks if regions 1 and 2 are similar. So is region 1 similar to region 2? The answer to that is no. The reason is region 2 is a quadrilateral, region 1 is a triangle, therefore it's impossible for them to be similar. They have to be the exact same shape. Part B says to name two similar triangles. And those two triangles are going to be triangle ADE and ABC, which are really the only two triangles in the figure. And the reason we know that is we have corresponding angles being congruent, and so we have angle, angle, angle postulate. Actually, I guess it's just angle, angle. But, anyways, they are similar. Okay, then after that, it asks us, what is the ratio of the areas of these two triangles? So, this is a great question. We know that these triangles are similar, right? And if we know that they are similar and we can find their scale factor, then we can use theorem 11-7 to guide us to what the ratio of their areas would be. So we know that this side length, AE, corresponds to the side AC. So we know the scale factor between these two triangles is going to be 2 to, not 3, but 2 to 5. Notice this entire length here is 5. So that is our scale factor. And once we have that, we can use theorem 11-7 to determine what the ratio of the areas is going to be. So the ratio of these areas is going to be the square of the scale factor. So it's going to be 2 squared to 5 squared, or 4 to 25. And that is our answer to part C. Now part D might get a little trickier. It's asking us to give the ratio of the areas between region 1 and region 2. Now note, these aren't similar figures, so we can't use our similar figure theorem, 11-7. But since we know what the ratios of these areas are, we can use our reasoning to figure out what the ratio of the two regions would be. So if we know that this total area, triangle ABC, is 25, say, square units, we know that region 1 is 4 square units, then we know that region 2 has to be the difference of that. So this is 25 minus 4, making it 21 units. And again, we don't know what the actual units are, we just know that the ratio is this. So we can kind of assign some arbitrary unit that we can use to play around with the areas here. So now this one's going to have to be 21, this one's going to have to be 4 because we determined that. And so all of a sudden we have the ratio of the areas is going to be 4 to 21. We just subtracted that 4 away from that whole region to give us kind of the area, I put that in quotes, area of region 2. So you're going to see several of these region problems in your homework, and just look at what you know and be prepared to figure out things in terms of ratios rather than in terms of exact areas. So like here, we don't know what the exact area of this is. It could be 4 square miles to 25 square miles, or it could be 8 square millimeters to 50 square millimeters. We just don't know. But we can still play around in terms of their ratios. So that's fun to do. Okay, that is all that I have right now. I hope that you enjoyed this lesson and have fun doing your geometry homework. Alright, take care.